Yes, Surya. Can you hear me clearly and see me clearly?
Yes.
And can you see the digital board?
Yes, sir.
Okay. See, although you are quite well versed or aware of the meaning of a function, we will go through it from some slightly different viewpoint. The aim of the course being to help you develop your mathematical intuition and also to develop your mathematical maturity. One of the other aims is that we are learning functions of several variables, that is advanced calculus or baby analysis, and we want to be able to get a geometric insight into it. Okay, that is what I mean by intuition. So I will go through some aspects of functions, and after that we will go to topology basics. Okay. So function, before we talk of a function, it deals with two sets, a domain and a range, or a codom or a domain and a codomain. The objects of functions are generally, when we say there is a function, from the set x to a set y. Here in analysis or advanced calculus, we deal with functions, points, numbers. The objects of a function could be anything like functions, points, numbers, sequence of numbers, so on and so forth. But in general, what I wanted to emphasize was that in general we can talk of any function as a mapping from a set of points to another set of points. So once again, if I belabor, if x itself is if the members of x of the domain are functions themselves, we can look upon those functions also as points. Okay. Follow the generic, very general meaning of a point. Okay. So okay, that's one thing. Another thing is that whenever we say A is a subset of B, we can also say, in other words, B covers A, or B contains A. Or B contains A. Okay, now apart from that, when we talk of functions, we'll talk of require sets. So sets, we know can be finite or infinite. Okay. Now finite sets can be listed or can be written in a roster form. A set consisting of, let us say, 1, 2, 3, 7. It can be explicitly listed. The members of the set can be listed. Or there can be a property, a set of even numbers lying between 2 to 14. But the infinite set is, we cannot list them. It is always better to write the property. Set theoretic description of the set. You understand what I am saying? It's the set of all points on the sphere. The set of all points on the sphere. We cannot list all of them.
Yes, sir.
Okay. Okay, now see, when we say a function from A to B, okay, or from the set En, Euclidean n space to Euclidean m space, it is what we call a mapping, okay, which is generally given by a formula. So what we have to understand here is that suppose P is a point of the domain, f of P is given, f of P is the value Can you see the screen?
No, sir.
I will call you again. Hold on. Can you see the screen now?
Yeah, so it's okay. Yeah.
Okay. So the function assigns to each point P in the domain a value f of P which is unique. It is so the function is the rule or the mapping, and f of P is the value. There are three things we are talking about: the value of the independent variable x, the value attained by it y, and the mapping. So this can be formalized this way: a function is an ordered triple, right? This is being abstract, taking it to the set theoretic manner. But the intuitive, what is a function? A function is basically a rule or a mapping. It is not f of P, remember that, which I think you know very well. Okay. Did you get your book Hoffman and Kunz?
No, sir.
What happened?
It was delivered.
It got?
I need to place the order again, sir.
Oh.
I don't know, there was some issue, the order was cancelled.
Oh, is it available in your campus store?
I know they came to sell a few books, the books that are related to our course, but I checked over there, so they didn't have that book. So
Oh, okay.
I need to reorder it.
Okay. Okay, now see, a function as a domain maps domain to range. Okay. Now, based on the nature of the domain is the classification of various functions.
Okay.
Functions like a function of one variable, one real variable, let us say, a function of two real variables, three real variables, right? You know what I mean. So f is a function. F is a function. In the first case, it is from E1 to R. In the second case, it is a function from the space E2 to R, so on and so forth. Okay, so we might say this, see, f of x, f of xy, and then we can say f of x, y, z. Okay, there's some disturbance today, I don't know what. Yeah, I checked my speed, it is 20 megabits per second.
Okay.
Anyway, it's okay. Yeah, the network is always having all sorts of problems. So again the board would have vanished, right?
Yes, sir.
Okay, I'll call you again. Okay. Is it loading now?
Yeah.
So a function of one real variable, two real variables, three real variables, but sometimes even though it might be a function of, in general, a point belonging to Euclidean n space where n is anything, any particular finite value, it is profitable to look upon all these also as functions of a single point or a single point P.
Okay.
Don't use the word number here, because the number is a real number, then it would create problems. It belongs to E1, the function. Okay, so for example, suppose we have a thin wire, very thin wire, and we are interested in the temperature distribution along the thin wire. So what is it? It makes sense to talk of f of p rather than f of x, y, z.
Correct.
Yeah?
Yes, sir.
Just as in electrostatics we have a a shell on which there is a distribution of electric charge, then we would like to know, we are interested in functions which are numeric valued, yet whose domain consists of points on the of the shell, on the surface of the shell.
Yes.
Right? Okay. Then why a function need not always be a numerical valued function. For example, let us say a particle is moving in any arbitrary fashion along 3D. Okay, so it is f of t equal to some point p in three-dimensional space, right? Right. So this might not be our only concern or a point of interest, because if the particle is subject to a magnetic field, we might be interested in the in the force at each point on the path of the particle, which in turn will make the function vector valued. So this then becomes the motivation to study functions which are not just numerical valued, only which might be functions in E2, E3, so on and so forth, vector valued functions. By the term vector now, we don't just associate, we don't just think of IJK.
Hello?
Yeah.
Sorry, sir.
That's okay. We don't think of a vectors.
Every point would have vector originated from that point.
Yeah, on the tangent to the path of the. Okay.
So not the tangent. I mean, the f of t would represent the locus of the point, how it moved in space, and every point on it would have a vector pointing towards the
direction of the intensity of the field or whatever. Yeah, that's it. So if you were to interested in the finding the force experienced by the particle as it moves along the path, we are essentially interested in a vector valued function, not just a numerical valued function.
Correct.
So that as an engineer might appeal to you. Okay? That why study vector valued functions? And now when we talk of vector valued functions, it is not just from the viewpoint of physics. Vector as in a used as in vector space. You are learning linear algebra. That is so now this is the motivation to study vector valued functions. Follow?
Yes, sir.
So now your horizons, your vistas have expanded. The term vector should bring the mathematical connotation into your mind, not just that Resnick-Halliday physics. Okay? So this then gives, see, when we represent when we think of a function which is of three variables as a function of a single point, we can bring geometry into play, because we can draw diagrams for a point moving or a function of a point. Sometimes we can draw diagrams for two-dimensional function, but beyond that it is very difficult.
Yes, sir.
Okay? One of the things that you will study soon is sequences and series. Sequences and series, their convergence and other things. So what is a sequence? A sequence is a function from the set of natural numbers to, let us say, the reals. At most we will study for complex numbers, a sequence which is complex valued, or a sequence which is real valued. So a sequence is represented this way: A sub n, n belonging to n. Right? But don't we say A1, A2, A3, A4 as a sequence?
Okay.
A sequence of numbers. No? So it is a function from n to the set of reals. Any sequence, when we talk about their convergence or limit of a sequence.
Yes, sir.
Generally in calculus we will be studying sequences and series first, and after that we will be discussing the concepts of calculus as applied to functions, continuity, differentiability, integrability, so on and so forth. Before that will come the similar notions, same notions applied to sequences and series. So a sequence is also a function, and this is the notation for a sequence. Sometimes see what is, since a sequence is a function, it will also have a range, right?
Yes.
Range. Now the sequence might just oscillate. You know the meaning of oscillate? Let us say a sequence, it just consider this sequence. This is also a sequence.
Yes, sir.
Okay? So the set of values it picks up is called trace. Here the trace of the sequence is just the set 1 and minus 1.
Okay.
Okay?
Yes, sir.
Next, we straight away come to topological ideas. There are some things about functions which I'll tell later, especially when we study curves and surfaces. Okay, which I'll tell later. So we come to topological ideas without very much worrying about the word topology. Topological ideas. See, generally topology deals with rigorous notions of the meaning of nearness, what is the meaning of interior or inside, so on and so forth. Put in another words, topology is a rigorous study of the limit point, of the abstract concept of the limit point. It is a very detailed study of the limit point. Put in another words here, topology concerns with the space in which continuous processes seem to occur. It formalizes the intuitive notion of space. Okay? Whereas geometry deals with rigid transformations of solid objects, transformations being reflections, rotations and translations. Properties which are invariant. See, when do we say that a triangle ABC is congruent to triangle PQR? Okay, you take this one of the triangles PQR, slide it onto this slide it onto it. If the edges and the vertices coincide, then we say that the two triangles are congruent. And geometry, plane geometry deals with properties which are invariant under these transformations. Right?
Yes.
Right. Now imagine that instead of paper triangles, we had rubber sheet triangles. A topology is known as rubber sheet geometry. Rubber sheet geometry. So we have to study properties which are invariant when you stretch the rubber. Let me know when the screen is loaded. Yeah. So when we stretch the rubber, twist the rubber, pull the rubber, or bend the rubber sheet figure. Stretch, twist, pull, bend, or cut the rubber sheet figure and then coalesce the same points, stitch the same points together again. When properties of these objects in topology, we study properties of these objects which remain invariant under these transformations. Okay, so that is a very rich viewpoint of topology, fun topology, as well as intuitive topology, intuitive concepts of topology. Okay. Well, that said, we start with the basic concept of neighborhood now. Okay. What is the meaning of neighborhood? When we say something applies to the neighborhood of a point, we mean it applies to all the things sufficiently, all other points sufficiently close to the given point. Right? Okay. When I'm repeating, when we say that something happens in a neighborhood of a point P0, we mean that it is true for all points that are sufficiently close to P0. Sufficiently. So we have to formalize this term. Remember how we studied limits?
Yes.
The concept of closeness. So now we come to, I will write the definition. The open spherical neighborhoods, the open spherical neighborhoods are the sets of the form all n equal to all points P in the space En with mod of p minus p0 less than rho, less than a distance rho, where rho is greater than 0. More generally, a neighborhood of P0 is any set More generally, a neighborhood of P0 is any set U that contains a spherical neighborhood of P sub 0. Okay. Now the term spherical need not be spherical. On the number line, it is just a interval. If En were, if we were discussing, right? If we were discussing,
Spherical would only be applicable in 3 dimensions. In real
no. I'll just hold on for a moment. It is just a word used in a special sense. I think this is, see, if we were to discuss functions or sequences from E1 to E1, from the reals to reals, the concept of neighborhood would still apply. Now the sphere would be an interval of line, a straight interval. We still call this a spherical neighborhood on E1. The term spherical specializes according to the dimensions, according to the domain, whether it is E1, E2, E3. So on the, supposing we were to discuss continuity on a plane, then a spherical neighborhood would be a small disk about P0. Okay. So in general, I mean, if you were to study topology, then the neighborhood could take a form like this also, like a square.
But they won't be equal.
No, I think this would be wrong. You cannot take it as square, because then
They won't be
they won't be equidistant. They won't be equidistant. Okay, it could be a sphere in 3D. It's a small golf ball sort of neighborhood. Okay. Now, when we talk of neighborhoods, and there are 3 relationships which come to our mind. So with respect to a set S, each point P has one of three relationships as follows. We say that P is interior to S if P belongs to S, if the point P lies in S and if S is a neighborhood for P. Thus, an interior point of S is surrounded completely by points of S. Next, we say that P is exterior to S if P does not, the point P does not lie in S, and if there is a neighborhood of P that is disjoint from S. So interior, exterior. What now? Interior and exterior are used in a special technical sense in math, right?
Okay.
We will, when we solve problems, it will become more clear.
So,
Yeah.
by definition of neighborhood, neighborhood include everything, like you said that a point is a neighbor, is in a neighborhood of another point P naught if P minus P naught mod is less than rho, where rho is some
Positive number. Right.
positive number.
So it is a like this. So P0 is here. The distance, all points P lying at a distance less than rho.
So rho is our own choice, and we could extend rho to any value.
Yeah. Generally we call them epsilon balls or epsilon ticks. Extremely small, epsilon is greater than 0. Just slightly greater than 0. We will play with it a lot.
We have the condition that rho should tend to 0.
No. There is no such condition. It is just epsilon greater than 0. It's an epsilon ball. So you will understand. I will explain you. I will give you examples.
Others will include the whole of the whole space, the whole n dimension.
Right. I understand your question. Good one. That is why we are studying neighborhood. Why? To formalize the intuition of closeness or nearness, which in turn will help us discuss continuity and hence discontinuity of functions and sequence functions. Right? We will come to it. We'll come to it. In fact, the analysis is called epsilontics. Surya, we will come to it. Okay, when we solve problems on continuity and related stuff, when we find limit points, isolated points. Okay. In fact, analysis is called epsilontics.
Okay.
It is also, I think I told you long back, it is the mathematics of very hard inequalities.
Yeah.
Yes, so your RMO training will help you a lot.
Okay.
So anyway, there is one more so finally we say that P is a boundary point for S if P is neither interior nor exterior to S. A boundary point, write down further, it is important. A boundary point may or may not belong to S. May or may not belong to S. We'll see examples. The set of all boundary points for S is called its boundary. Right? And we will use the notation del S for boundary. Notation del S. Okay? How is your linear algebra course going on? Are you enjoying it?
Yes, and it's fine. Right now in the previous lecture we defined linearly dependent and independent vectors.
Yes.
And we just gave a few examples. So it's fine till now.
Okay, it's going a bit slow though. Going a bit slow. I told you, if you use Gilbert's strength, you will become slow in life. I don't like that guy. It is good. He is a very great mathematician, but it is. But then you see, the thing is that when you want to teach a mass of 30-40 students, you have to design the course and write the book in a different manner. And of course, I don't. The IT mathematicians are great themselves; they are immortal giants. But they would have their own reasons for selecting that book. But for you, it won't be. You start going through that Hoffman and Kunz. You can pick it up from the library also. In fact, it's a must course for CS guys. Without linear algebra, there is no CS. So it's called. I will show you a figure. I'll draw a figure, and we will try to find the boundary of that set. Here is a point P. This is the set S. The set S also contains this point P. It contains this point Q. Okay?
Okay.
No, my I think this figure illustrates Q is in interior of S, P is exterior to S, and points which neither belong to this part nor this region form the boundary. So the boundary does agree with the intuitive notion of boundary in most cases. Now see, but need not be so. Let S be the set consisting of just 2 points 0, 0 and 1, 0 in the plane. Then what is the boundary of the set? Set S consists of 2 points 0, 0 and 1, 0 in the plane. What question? What is the boundary of this set? Refer to the definitions and try to answer it. Come on, let's see.
So the points themselves are the boundaries, and there's nothing defined as an interior to the set.
Excellent. Next, a set is said to be open if every point of S is interior to S this is the same as saying this is the same as saying that no boundary point of S belongs to S. So this is left as an exercise 14 in the homework on topological ideas. Next, a set S is said to be so open is like, what does open remind you of? Does it ring a bell? Remember open intervals? X to Y,
Yes, sir.
minus infinity to infinity. This is open
There's
interval.
no boundary.
Okay?
Yes, sir.
Then there are closed intervals also. So similarly, a set S is said to be closed if every point that is not in S is in fact exterior to S. This is same as saying which is left as an exercise, same as saying every boundary point of S is in S itself. Remember when we wrote the definition of boundary point, we said the boundary point need not belong to the set.
It's more than next.
Yes.
So this.
Yeah.
Okay. Right. Got it.
Okay. So all your ideas will start converging after a few months.
Okay.
Supremum and other things, everything will converge soon. It will take a while though. And I will also teach you something from Rodin so that your rigorous mathematics starts developing. Okay, we'll stop here, beta.
Okay.
And there is no homework. No homework yet. I sent you 2 assignments today, but you cannot attempt them yet. More information, knowledge is required to attempt those.
Okay.
Okay then. Bye bye now. You may just revise the lecture notes.
Yeah, I'll do that.
Okay. Bye bye. Good night.
Bye, sir.